stretched across the vast reaches of space. The James Webb Space Telescope, a marvel of human ingenuity, peers into the cosmic void. On one fateful night, it captures something peculiar. In the distant orbit of Proxima Centauri, a small planet, Proxima Centauri b glows faintly in the darkness. But this is no ordinary glow. It's not the light of stars, nor the reflection of a sunlit surface. No, these glimmers are different, organized, structured. Almost like the streetlights and buildings of a city, as seen from space. Could it be that what we are witnessing is a civilization illuminating its world, just as we illuminate ours? Or is it something far more mysterious, a phenomenon we have yet to comprehend? As the data unfolds, scientists are faced with an extraordinary question. Are these lights the first tangible proof that we are not alone, or a mirage, a trick of nature's hand, playing with our hopes and our dreams? Whatever it may be, the mystery deepens as the telescope continues to monitor these enigmatic signals from 25 trillion miles away. Proxima Centauri b, the closest exoplanet to our solar system, orbits a dim red dwarf star. Proxima Centauri, just 4.24 light-years away. This tiny world caught in a tight orbit endures extreme conditions. Its proximity to its host star subjects it to intense solar radiation and powerful winds, creating an environment unlike anything Earth has ever experienced. The planet is likely tidally locked, with one side forever facing its star in perpetual daylight, while the other remains shrouded in eternal darkness. This creates two vastly different worlds. On the same planet, one side scorched by intense heat, and the other plunged into a frigid abyss. But here's where it gets fascinating. The lights detected on Proxima Centauri b appear to originate from its dark side. This challenges everything we know about planetary science. How could such organized illumination exist on the night side of a planet that should be frozen and barren? Scientists speculate that if Proxima Centauri b possesses even a thin atmosphere, it could redistribute heat from the day side to the night side, allowing for more stable conditions that might support complex processes or even life. But the absence of an atmosphere would mean these lights, if real or artificial, crafted by an intelligence capable of surviving and thriving under extreme cosmic conditions. Whether these lights are natural phenomena or a technological marvel, the possibilities they open up are as vast as the universe itself. As the telescope continues its observations, we find ourselves on the brink of discovery, teetering between excitement and the fear of an answer that might change our understanding of the cosmos forever. The James Webb Space Telescope represents the pinnacle of human achievement, designed to see beyond the limits of what our eyes can perceive. With its advanced infrared sensors, this technological marvel looks deep into the cosmos, peering through clouds of gas and dust to reveal the hidden secrets of distant planets. But what makes the telescope truly remarkable is its ability to detect subtle changes in light, even from planets orbiting other stars. In the case of Proxima Centauri b, its precision allowed scientists to pick up faint, organized glimmers that resemble the artificial lights of cities on Earth. This was no coincidence. The telescope is specifically designed to pick up infrared signatures, making it ideal for studying planets with potential signs of life. By capturing infrared light, the telescope can detect heat patterns and study the atmospheric composition of distant worlds. These capabilities enable scientists to distinguish between natural light, sources like a planet reflecting its star's light, and artificial illumination. This ability is critical, as it may allow us to determine whether the lights on Proxima Centauri b are a result of geological processes, atmospheric phenomena, or something far more intriguing. It's not just about observing the lights themselves, but analyzing the wavelengths of light passing through a planet's atmosphere. Each element leaves a unique fingerprint, a spectral signature that reveals its composition. The James Webb Space Telescope can identify these markers, searching for clues such as water vapor, carbon dioxide, or even traces of industrial chemicals that might indicate intelligent activity. Through the telescope's data, scientists are able to build a more detailed picture of Proxima Centauri b, whether it's a lifeless rocky planet or a world teeming with possibilities. The precision of the telescope's instruments pushes the boundaries of what we know, hinting at a future where distant worlds are no longer just specks of light, but places with stories of their own, waiting to be uncovered. While the discovery of lights on Proxima Centauri b has sparked worldwide excitement, it has also ignited intense debates. Within the scientific community, could these lights truly be evidence of an intelligent civilization, or are they merely natural phenomena that challenge our understanding of planetary science? Some experts suggest the lights could be the result of geological activity, volcanic eruptions releasing luminous gases into the planet's thin atmosphere. Others propose that the planet's interaction with its host star creates a glow similar to the auroras we see on Earth, a spectacle of light caused by the solar winds. Yet the pattern of these lights remains distinct. Too consistent, too structured. It raises the question, if these glimmers are truly artificial, who or what is creating them? And if this is evidence of technology, then we may be facing the most profound discovery in human history. Plans are already underway to probe further into this enigma. Missions are being designed to closely observe Proxima Centauri b, but the journey is fraught with challenges. The intense radiation from its host star and the sheer distance make it a technical feat, beyond anything humanity has attempted before. As scientists work through the data, each flicker of light becomes a focal point of debate. Could these be signals? A communication attempt from an advanced civilization? Or is it simply our interpretation, driven by the human desire to not be alone in the universe? Every observation reveals new mysteries and new questions. What message might these lights hold? If any, as the telescope continues its vigilant watch, scientists remain divided. For some, it is a hopeful sign, while for others, it is a puzzle that will take decades to unravel. The discovery of lights on Proxima Centauri b, whether they are artificial or natural, presents an extraordinary opportunity, a chance to redefine our understanding of the universe and our place within it. It raises profound questions about life beyond Earth. Are we truly alone? Or is the cosmos teeming with civilizations, hidden just beyond our reach? For centuries, humanity has gazed into the night sky, wondering if there are others out there, perhaps sharing the same hopes and dreams. While the James Webb Space Telescope has given us a tantalizing glimpse into the mysteries of Proxima Centauri b, the journey is far from over. The next chapter in space exploration demands even more advanced technology. Innovations that will allow us to pierce the cosmic veil and uncover the secrets hidden in the light of distant stars. The extremely large telescope, set to begin operations within the next few years, promises to be the most powerful tool yet for observing planets like Proxima Centauri b, with a mirror diameter stretching over 39 meters. This groundbreaking instrument will have the resolution needed to study planetary atmospheres in detail, allowing us to search for signs of life and analyze the chemical makeup of faraway worlds. But it's not just about bigger telescopes. New technologies, such as starshade missions and coronagraphs, are being developed to block out the overwhelming light of stars, much like shading your eyes from the sun, so we can see the faint reflections from planets. These tools will help astronomers study the light signatures from planets and identify molecules that could hint at life. The combination of these technologies will allow us to capture direct images of planets within the habitable zones of their stars, opening the door to detailed atmospheric studies. Imagine being able to see the colors, the heat patterns, and even the cloud formations of worlds, light years away, all from the comfort of our telescopes. Yet the ultimate goal remains the same: to find planets that could host life. The data we collect will not only refine our understanding of planets, like Proxima Centauri b, but also provide insights into the countless other worlds that orbit stars across our galaxy. Collaborative efforts across the globe are paving the way for missions that may one day send probes, or even crewed spacecraft, to our nearest stellar neighbors. From AI-powered spacecraft, capable of navigating interstellar distances, to robotic explorers, designed to survive extreme environments, the future of space exploration is filled with possibilities. As we prepare for these ambitious missions, humanity stands on the brink of an era where interstellar travel could transform science fiction into reality. The lights on Proxima Centauri b, whether they are beacons of a distant civilization or natural phenomena, have sparked a new wave of exploration that will push the limits of our technology and our imagination. Here on Earth, life has proven itself to be astonishingly adaptable. Extremophiles organisms that thrive in environments once thought uninhabitable live in deep ocean vents, acidic hot springs, and even radioactive wastelands. If life has evolved under such extreme conditions, on Earth, what might it look like? On a planet orbiting so close to a dim, red star, imagine a world where organisms have developed bioluminescence to survive in the eternal night, a way to generate their own light in the absence of sunlight. Perhaps they harness energy from geothermal vents, or adapt to the fluctuating radiation levels on the sunlit side, developing protective mechanisms that Earth's life forms could never conceive. We may be small in the vast expanse of the cosmos, but our curiosity knows no bounds. The lights on Proxima Centauri b, whether they signal an alien civilization or a natural wonder, are a call to adventure, a reminder that the greatest discoveries often lie beyond the horizon, waiting for those bold enough to seek them. In the constellation Cygnus, roughly 700–800 light-years from Earth, lies one of the universe's intriguing cosmic landmarks. V404 Cygni, known for its intense eruptions of energy, when the black hole draws material from its companion. This typically results in immense bursts of energy and light, offering a vivid display of gravitational forces in action. Recently, V404 Sigma revealed something unexpected. It isn't a simple binary system as previously thought. New observations reveal it as a rare triple system, with a third stellar companion orbiting the black hole and its close partner at an astonishing distance. This newly identified third star circles around the inner binary, adding depth to the structure and complexity of V404 Cygni. This stellar system has long been known for its inner binary structure, where a black hole and a neighboring star orbit each other. The black hole, an extremely dense remnant of a massive star, exerts a powerful gravitational force on its companion, a star with characteristics similar to our Sun. This dynamic pairing leads to what is known as an accretion process. As the black hole draws material from the outer layers of its companion, the matter heats up, spiraling toward the black hole in a swirling disk known as an accretion disk. This process not only results in the release of high-energy particles, but also produces intense flashes of light and X-rays, detectable from Earth, the orbits in this binary relationship are remarkably close, with the black hole and its star companion completing an orbit every 6.5 days. This tight orbit amplifies the accretion process, causing frequent eruptions of energy that, while relatively brief, are powerful enough to be observed by telescopes. Even from such a great distance, these observations have provided astronomers with insights into the behavior of black holes within binary systems and have contributed significantly to our understanding of how black holes interact with other celestial bodies. Scientists believe that studying systems like V404 helps explain similar cosmic events and processes across the universe. Recently, scientists using advanced observation techniques uncovered a surprising third component in the V404 system. This third star, unlike the two members of the inner binary, orbits at a considerable distance, about 3,500 times the distance from the Earth to the Sun. It completes an orbit only once every 70,000 years, making it the outermost member of this rare, triple configuration. This discovery redefines V404 Cygni as it shifts from a typical black hole binary to a hierarchical triple system, with two components tightly bound in a distant third companion on a much longer orbit to detect this outer star. Researchers utilized precise imaging techniques, relying on data from telescopes, capable of capturing minor distortions in the system's light patterns. These subtle shifts provided clues that something beyond the inner binary was influencing the gravitational dynamics at play. As the first black hole system of its kind to be observed, V404 Cygni now offers a unique example of how multiple stars might interact with a black hole over enormous distances. The presence of this third star challenges traditional theories about the formation and stability of black hole systems, suggesting that such systems may have formed differently from other black hole binaries. Traditionally, black holes were thought to form from supernova explosions, cataclysmic events that result in the remnants of massive stars collapsing. The intense energy released during these explosions would generally disrupt the surrounding stellar structures, making it difficult for any nearby stars to maintain stable orbits. However, in the case of V404 Cygni, the presence of this third star, orbiting at such an expansive distance, suggests an alternative scenario. One hypothesis gaining traction is that the black hole in V404 Cygni may have formed through a direct collapse, rather than a supernova. This means that instead of exploding, the massive star that eventually became the black hole might have gradually imploded, avoiding the shockwaves that usually accompany a supernova. This gentler formation process would allow a distant companion, like the third star in V404 Cygni, to maintain its orbit without being ejected or disrupted. If correct, this theory would indicate that black hole systems can evolve in ways previously unconsidered, potentially leading to the discovery of more quietly formed black holes with companion stars that survived the process. Beyond the structural insight, this discovery has implications for black hole research. As a whole, understanding the different ways black holes can form helps astronomers refine models of stellar evolution and gravitational dynamics. The unique configuration with its stable third star orbiting a powerful black hole might serve as a blueprint for identifying similar systems. It also raises questions about how many black holes in our galaxy may have formed through this gentler process, and what that means for the diversity of black hole systems within the Milky Way and beyond. The discovery of this unique system has opened up new horizons in black hole research, sparking interest in finding more examples of such unique configurations. Scientists are eager to explore whether other black holes might also form in similarly quiet processes, keeping their companion stars intact rather than expelling them. Future observations and studies on this triple system could provide more answers, allowing researchers to probe deeper into questions about black hole origins and evolution. By mapping out the orbits and movements of the three components in V404 Cygni, they hope to gain clearer insights into how gravitational forces operate in complex black hole systems. These findings may lead to refined models of black hole formation, and perhaps reveal additional systems with similar structures across our galaxy as scientists continue their search. V404 Cygni stands as a testament to the surprises that space still holds. This discovery is just one chapter in the ongoing story of black holes, and it leaves us with a sense of anticipation for what might come next in our exploration of the universe's most mysterious entities. Forget everything you thought you knew about the universe. What if a telescope found a signal that could mean life or a galaxy that shouldn't exist? We're not dreaming anymore. The James Webb Space Telescope is rewriting the rules. It's not just looking at stars. It's staring into the past, pulling up data that makes scientists question everything. Galaxies forming before they had time. Planets with chemicals that scream life. Structures too perfect for a chaotic cosmos. This isn't science fiction. It's real measurable, and it's shaking our understanding to the core. The universe isn't playing by our playbook. It's showing us a cosmic puzzle, and the pieces don't fit. Webb's infrared eyes are catching things we can't ignore. From signals 124 light-years away to galaxies born when the universe was a baby. We're not just finding answers. We're finding questions we didn't know to ask. Today, we're diving into 4 discoveries that turn it all upside down. A planet with a gas that might mean life. A spiral galaxy that looks like home way too early. Auroras on Neptune that don't add up. And galaxies so old they break the timeline. This is the universe talking. And it's not whispering. It's shouting. Stick with us to see what Webb found and why it changes everything. What if a planet 124 light-years away is breathing? The James Webb Telescope found something on K2-18b that's hard to explain. K2-18b isn't just another dot in the sky. It's an exoplanet orbiting a dim red dwarf, sitting in the sweet spot where water could stay liquid. For years, it was just interesting. Too big to be like Earth, too far to make headlines. Then Webb turned its mirror, and everything changed. It scanned the planet's atmosphere, sifting light for chemical clues. What it found stopped scientists cold: dimethyl sulfide. On Earth, this gas comes from life. Tiny ocean creatures like plankton pump it out when they die. It's the smell of salty sea air, sharp and fleeting. Sunlight burns it away fast, so it needs constant replenishing. By life, Webb caught this signal in K2-18b's skies. Not a whisper, but a shout. The levels were high, way higher than Earth's. Think of it like spotting smoke from a fire across the galaxy. You don't know what's burning, but something's alive. This planet has a thick, hydrogen-rich atmosphere, probably cloaking a deep ocean. If life's there, it's not fish or forests. Maybe microbes floating in that alien sea churning chemicals, or something we can't even picture. The signal's strong enough to suggest more than a few specks. It could be an ecosystem, a living world pumping gas on a massive scale. But hold on, science doesn't jump to aliens. There's a catch. Other chemicals like methane can mimic this signal in infrared. Mistakes happen, so they checked again. The signal didn't fade. It got clearer. Stronger, estimated at 1,000 times Earth's levels. That's not a glitch. That's something real. Now, could it be geology, a weird volcano, or gas pocket? Maybe. But on Earth, nothing non-living makes dimethyl sulfide like this. We've looked. No dice. If K2-18b's doing it without life, we need a new rulebook. This is where the cosmic puzzle gets wild. K2-18b isn't some distant theory. It's 124 light-years away, close enough to study, far enough to haunt us. If this is life, we're not talking fossils or dreams. We're talking something alive right now, leaving its mark in the sky. Webb's data is solid, but it's not the final word. More checks are coming. Other telescopes, other teams. They'll rule out every trick, every false alarm. Chemistry, physics. If nothing else fits, we're left with one answer: life. That changes everything. We're not just asking if we're alone. We're measuring what else is out there. What's its chemistry? How does it survive? Is it like us or something stranger? K2-18b's signal is a piece of the puzzle, and it's screaming for attention. We used to think alien life was a future problem, something for starships or science fiction. But now it might be staring us down. A signal from a planet we can almost touch. This isn't the end of the story. It's the start. K2-18b's signal hints at life. But what if the universe built galaxies too perfect for its own rules? What if a galaxy looked like home, but showed up billions of years too early? Webb found one, and it's turning our timeline upside down. Meet Zulong, or Torch Dragon, a spiral galaxy spotted by the James Webb Telescope. It's not just far away. It's far back, shining from when the universe was barely 1 billion years old. That's not long after the Big Bang, when everything was supposed to be a mess. Picture the early cosmos like a stormy sea with gas and stars crashing, merging, tearing apart. Galaxies back then should be chaotic blobs, not orderly spirals like our Milky Way. Spirals need time. Time for gravity to settle, for stars to align into neat arms, for a disk to spin steady. That takes billions of years, or so we thought. Zhulong breaks the rules. It's got those arms that balance that structure. It looks like it's been chilling for ages, not freshly born in a cosmic riot. Think of it like finding a polished statue in a quarry where rocks are still being blasted. It shouldn't be there, but Webb's infrared eyes caught it clear as day. The light we're seeing left Zhulong when the universe was a toddler, yet it's already grown up. Its spiral arms are tight, its core is bright, and it's stable. That means it formed even earlier, maybe just a few 100 million years after the Big Bang. Here's the science. We measure this distance with redshift. It's how light stretches as the universe expands, pushing starlight to redder colors. Zhulong's redshift puts it at 12.5 billion years away. That's not just a number, it's a problem. Our models say spirals come late after messy galaxies collide and cool. Zhulong says otherwise. It's not alone either. Webb's finding more like it galaxies too neat for their time. This is another piece of the cosmic puzzle, and it's not fitting. Why does this matter? If spirals formed this fast, the universe was cooking way sooner than we thought. Maybe gravity worked harder back then. Maybe dark matter, that invisible glue, pulled stars together like a magnet on steroids. Or maybe our whole timeline's off. Some scientists are rethinking how gas clumped in the early days. Others wonder if the first stars burned out faster, spitting out material for galaxies like Zhulong. The wilder idea: the universe's rules might have been different back then. Not by much, but enough to rush things. This isn't just about one galaxy. It's about what's possible. Spirals like Zhulong are stable. They're the kind of places where stars last, where planets form, where life might get a shot. If they were around, this early, life-friendly spots could have popped up way before we expected. That's big. It means our Milky Way, our home, isn't so special. It's just one of many, maybe late to the party. Zhulong's telling us the universe didn't waste time. It was building homes while we thought it was still setting up shop. Webb's not done. It keeps spotting these early spirals, each one a jab at what we thought we knew. Zhulong's not an outlier. It's a clue. A clue that the cosmic puzzle has more pieces than we guessed. We're not just looking at a galaxy, we're looking at a universe that's been ahead of us from the start. And that's what makes this so unsettling. The past looks too much like now. Zhulong's early spiral defies the stars, but what's hiding closer in our own cosmic backyard? The James Webb Telescope turned to Neptune, and it's not what we expected. Neptune's the loner of our solar system. Far out, cold, dark, and barely studied. Most of what we know comes from one quick visit by Voyager 2 in 1989. Since then, it's been blurry glimpses through ground telescopes. Nobody thought to point Webb, our deep space champion, at a planet next door. But they did. And what it saw wasn't just pretty lights. It was a puzzle piece that doesn't fit. Webb caught Neptune's auroras glowing at its poles, not like Earth's northern lights, all soft and shimmery. These are wild, chaotic, driven by forces we don't fully get. Think of it like finding a strange signal on a radio you thought was broken. Something's broadcasting and it's loud. Webb's infrared vision cut through Neptune's haze, mapping heat and chemistry in ways we've never seen. It spotted auroras pulsing with weird patterns, hot spots where there shouldn't be heat, cold patches that defy the sun's weak grip out there. On Earth, auroras come from solar wind-charged particles slamming into our magnetic field. Neptune's got a field too, but it's a mess. Tilted, lopsided, nothing like ours. Those particles take forever to reach it, crawling through space from the sun. Yet Webb saw something else. Temperature swings that don't add up. Some areas cooled too fast. Others burned hotter than they should. It's like Neptune's cooking its own weather and we don't know the recipe. Here's the data. Webb's instruments tuned for distant galaxies picked up chemical shifts in Neptune's atmosphere. Methane absorbs light in weird ways, but something's tweaking it. Maybe magnetic storms. Maybe reactions we haven't pinned down. The auroras aren't just a light show. They're clues to a planet we thought we knew. Neptune's magnetic field is a beast, twisting in ways that mess with our models. Those hotspots could be energy leaking from inside the planet. Those cold zones, maybe gas sinking in ways we didn't expect. We're not sure. And that's the point. Webb didn't just snap a picture. It raised questions we weren't asking. This isn't about some far-off star. It's right here in our own system. Neptune's been out there keeping quiet while we chased galaxies. Now Webb's showing us we missed something. The sample mentioned Voyager's flyby, but Webb's look is sharper, deeper. It's not just auroras. It's a planet acting alive with storms and heat and chemistry that don't play by our rules. And it's not alone. Uranus-Neptune's twin might be hiding similar tricks. We haven't looked hard enough. Our outer planets are strangers, and Webb's proving it. Why does this matter? It's another crack in the cosmic puzzle. We thought we had our solar system figured out. Earth, Mars, Jupiter done. But Neptune's saying, hold up. There's more. Its auroras hint at forces magnetic, chemical, maybe even geological, that could teach us how planets work. Not just here, but everywhere. If we're wrong about Neptune, what else are we missing? Moons with oceans. Weather we can't predict. This isn't just a pretty view. It's a wake-up call. The universe doesn't stop surprising us even in our own backyard. Webb's not done with Neptune. More observations are coming. Maybe they'll crack the code on those auroras, or maybe they'll dig up new mysteries. Either way, this telescope's rewriting what we thought was settled. It's telling us to look closer, even at the places we thought we knew. Neptune's auroras aren't just lights. They're a signal. Something's going on out there, and we're just starting to listen. Neptune's auroras glow with secrets. But what if galaxies formed before they were allowed? The James Webb Telescope found some, and they're breaking every rule. Say hello to JWST Z14-0. It's not just a galaxy, it's a time bomb. Webb spotted it shining when the universe was only 280 million years old. Back then, the cosmos was a hot mess. Gas swirling stars, barely sparking matter, still figuring itself out. Galaxies weren't supposed to happen yet. They need time. Time for gas to cool, for stars to clump, for gravity to sculpt something solid. Picture it like trying to bake a cake in a microwave that's still warming up. You shouldn't get a cake. But JWST Z14-0 is no raw batter. It's a full-on galaxy compact, bright, packed with millions of stars. This is nuts. Our models said galaxies take billions of years to get their act together. First you need stars, tiny ones made of hydrogen and helium burning fast and dying young. They explode, spitting out heavier stuff like carbon. That stuff cools, collapses, forms new stars, and slowly builds galaxies. JWST Z14-0 laughs at that. It's got structure, mass, and shine all before the universe even had a chance to stretch its legs. Think of it like finding a skyscraper built before the invention of steel. Webb's got the receipts. It measures this with redshift. JWST Z14-0's redshift screams 13.5 billion years old. That's not just far, it's impossible. Or it was. This galaxy's got a mass of 100 million suns squeezed into 500 light-years. It's small but mighty, and it's not alone. Webb's finding more like it galaxies popping up way too early, too bright, too big. This is where the cosmic puzzle cracks open. Something sped things up. Maybe dark matter, that invisible scaffolding, yanked matter together like a cosmic tow truck. Maybe the first stars were giants blowing up fast and seeding galaxies in a hurry. Or maybe the universe's early rules were looser, gravity stronger, time weirder. Scientists are scrambling. Some say gas clouds collapsed faster than we thought. Others think dark matter played a bigger role. The wild ones, they're whispering about new physics stuff we haven't dreamed up yet. Why is this a big deal? These early galaxies aren't just old, they're game changers. If they formed this fast, the universe was ready for business way sooner than we planned. Stable galaxies mean stable stars. Stable stars mean planets. Planets mean chances for life way back when we thought the cosmos was still in diapers. JWST Z14-0 isn't just a pretty dot. It's a clue that the universe didn't wait around. It was building fast while we were busy writing rules it doesn't follow. Webb's stacking up these finds, more early galaxies, each one a jab at our timeline. They're not flukes. They're a pattern, The cosmic puzzle keeps growing, and this piece is heavy. It's telling us the universe was never slow. It was always in a rush, spinning out galaxies like it had somewhere to be. And that's what's spooky. We thought we knew the story of the cosmos. But JWST Z14-0 says we're reading the wrong book. Webb's not just showing us stars, it's showing us how much we've got to learn. Early galaxies flipped the script. But what does it all mean for us? The James Webb Telescope's rewriting our place in the cosmos. Look at what we found. K218b's got a gas that might mean life pumping out signals we can't ignore. J-Long's spiral showed up way too early, looking like home, before it should. Neptune's auroras are dancing with secrets right in our backyard. And JWST Z14-0, that galaxy born too soon, says the universe was in a hurry. These aren't just dots in the sky. They're pieces of a cosmic puzzle, and they're telling us something big. The universe isn't what we thought. It's not slow, not empty, not quiet. It's been busy building galaxies, maybe even life, long before we had a clue. This changes the game. We used to ask if we're alone. Now we're asking how many others are out there. Are we just one piece in a massive puzzle or something special? Webb's data doesn't shout answers. It whispers hints. Galaxies too old. Signals too strong. Lights too weird. Each one's a crack in what we thought we knew. And it's not over. More discoveries are coming. More questions. More pieces. So what now? Keep looking up. The universe is talking, and we're finally listening. Not with dreams, but with hard data. Webb's showing us a cosmos that's alive, restless, and full of surprises. Are we ready to find out what's next? The puzzle's not solved. It's just getting started. Some stars are so massive, so luminous. They could swallow our entire solar system and still have room to breathe. Tonight, you'll drift past them, not as an observer, but as a traveler. These are the behemoths, cosmic titans that live fast, burn furiously, and explode with enough energy to shape galaxies. And somewhere in their death is the reason you exist. And some of these stars, they're colossal. If seen clearly, one would engulf Mercury, Venus, Earth, and even Mars. These are the titans you came to meet. Despite their grandeur, these giants are fleeting. They live fast and die spectacularly, returning their matter to the universe that gave birth to them. As you drift closer, you begin to understand they are not just fascinating. They are foundational. Without them, you wouldn't be here. Their collapse forged the elements in your bones, your blood, the air you breathe. You are quite literally made of star stuff. So before you settle in, if journeys like this mean something to you, consider liking the video and subscribing, but only if you genuinely enjoy this kind of voyage. And I'd love to know, where are you watching from? And what time is it right now? Now, dim the lights. Maybe turn on a fan for that soft hum, and let's begin tonight's journey. You start in a quiet corner of our galaxy, near the local neighborhood of stars. Through the lens of space, even nearby suns seem faint. Their light has traveled for years to reach you, moving at nearly 300,000 kilometers per second. Out here, distance is time. 1 year of light travel equals nearly 10 trillion kilometers. It's a number so large, it slips away from grasp. So when you gaze at JWST, the giant star we'll meet tonight, you're seeing it not as it is, but as it was, almost 10,000 years ago. And when you arrive at its doorstep, what greets you isn't fire. It's haze, a deep red fog, like a slow breath, exhaled by the universe itself. The star is old, massive, a red supergiant that once blazed blue in its youth. Over millions of years, it swelled outward, its core still fusing elements in violent heat. Hydrogen to helium, helium to carbon, carbon to oxygen. Like layers in a cosmic oven, its surface isn't solid, but roils with convective gas. Bubbles the size of planets rise and fall. Like boiling water, the outer layers are barely held together. Gravity and radiation, locked in a fragile, flickering dance. Even from millions of kilometers away, the heat would unmake you. And yet, you feel calm, small, in the best possible way. not diminished, but placed in scale. A quiet thought passes through. How many of these giants float in the Milky Way alone? Tens of thousands, maybe more, most hidden behind dust and silence. Even now, drifting near JWST, you see the night isn't black, it's velvet, deep, laced with soft radiation, the afterglow of ancient energy, cosmic microwave background, ionized hydrogen, light from galaxies too far to resolve. Some astronomers still debate whether JWST is truly the largest. Stellar measurements are delicate. Dust mass loss and distance skew the numbers, but that's not what matters. What matters is this: you're floating beside a thing so vast, even your imagination struggles to grasp it. And this is only the beginning. Ahead, more giants await. You begin to understand how far and how bright these behemoths shine across interstellar space. You drift slowly as if weightless on a current of thought and photons. The distances between stars stretch like taffy pulled across eons. There are no hard lines in space, only gradients between heat and cold light and shadow time and timelessness. Light, the quiet courier of space, is your guide. It reveals not only where a star is, but when it was. This simple idea becomes profound out here. To look at the stars is to peer into the past. Every twinkle you remember seeing from Earth is ancient. Even the nearby Alpha Centauri system is more than 4 years gone by the time its light touches your eye. For behemoth stars, this becomes even more powerful. Their light can stretch across entire galaxies, even briefly outshining all the other stars combined. These are luminous giants, massive bodies whose brilliance is not merely for show, but a byproduct of immense energy and violent fusion. And yet, even the brightest among them are dwarfed by the scale of interstellar space. Light moves fast, but the cosmos expands faster still. You float past a point where the light from one star, one magnificent swollen supergiant, has been traveling for 10,000 years and is just now passing by your invisible shoulder. The brightness of a star isn't just about its actual power. It's about perspective, its luminosity, versus its apparent brightness. A nearby candle can outshine a distant bonfire. But astronomers have learned to disentangle this illusion using the inverse square law of light. Each doubling of distance makes the light appear 4 times dimmer. So when you see a star like R136A1 burning at its core with temperatures over 50,000 Kelvin, you know it must be truly luminous to appear as bright as it does from Earth. Another star, Deneb, a blue-white supergiant in Cygnus, is so bright it rivals other nearby stars. Even though it's nearly 2,600 light-years away, its light left around the time ancient Mesopotamians were building ziggurats. And only now it reaches us, quietly, consistently. A reminder that space is not empty. It is full of stories told in photons. You imagine yourself traveling at the speed of light. Even then you realize it would take years to traverse just this quiet arm of the galaxy, across the Milky Way over 100,000 years. And yet light makes this journey, every second, without fatigue. No vessel, no engine, just momentum and time. And as you float, you start to sense a subtle truth. That starlight is the language of the cosmos. Every wavelength carries a message, a temperature, a speed, a chemical signature. And like a quiet archivist, the universe records its story in spectra. One such story lies ahead. You notice it even now before you reach it. A faint crimson halo on the edge of darkness. The telltale glow of hydrogen alpha emissions filtered through interstellar dust. It marks the domain of another giant. You slow your pace, not from fear but from reverence. Because the star ahead, Stephenson 218, exists at the very boundary of known stellar dimensions. Some models suggest its radius is over 2,100 times that of the Sun. If placed in our solar system, its edge would stretch past the orbit of Saturn. And yet, you could fly past it and never truly see it, because it is cloaked, hidden, a ghost, in the haze. Before you approach your thoughts, linger on the scale of this moment. You've traveled dozens of light years already, maybe hundreds, and still, you've only met a few members of this rare family of giants. Most stars in the universe are small, dim, and long-lived, like red dwarfs quietly burning for trillions of years. But here you are among the loudest, shortest-lived fires, stars that shape galaxies, stars that will soon vanish, leaving only dust-heavy elements and gravity behind. There's a subtle ache in this realization. That brilliance doesn't last, that the most powerful lights fade fastest, and yet that too is natural. That too is beautiful. Some astronomers believe the upper limit of stellar size is still not well understood. We can model fusion and gravitational balance, but turbulence, magnetic fields, and stellar winds complicate the math. Observations help, but stars like Stephenson 218 lie buried behind veils of interstellar gas, visible only in slivers of infrared and radio data. Some question its precise size. Some argue it could be a cluster, but for now, it holds a kind of quiet throne in our records. A record, not of ego, but of scale. As you prepare to approach, the light grows redder, deeper. Dust scatters short wavelengths, letting only the longest, warmest reds pass through. It's like drifting into a sunset that never ends. And even now, space holds its silence. No roar of fusion, no flicker of noise, just starlight, stretching into forever. You encounter Scuti, an immense red supergiant near the edge of known stellar scale. You arrive without a sound, slipping into the quiet reach of Scuti's domain. There is no firm edge to cross, only a gradual swelling of light and warmth, thick as breath. You hover now near one of the largest stars ever measured by volume, a red supergiant residing in the constellation Scutum, about 9,500 light-years from Earth. The star is not bright in the visible sense. Its energy is stretched and spread, softened by the sheer distance, and by the dust that floats between galaxies like fine smoke. What you see is not blinding, but warm. It glows in the deep red and infrared parts of the spectrum, casting a long, lazy light across the emptiness. Scuti is a strange place to imagine. A single object, and yet its surface would engulf the orbits of Mercury, Venus, Earth, and Mars. Light takes more than 7 hours just to travel from one side of it to the other. And yet it is not a solid thing, not even a clearly defined one. Its edges blur into the vacuum. Its atmosphere is a dance of heated gas, always rising, falling, and leaking away into space. Inside the vast convective layers of this star, pressure and temperature are constantly fighting gravity's slow pull. The outer layers swell because the radiation generated deep in the core is strong enough to push them outward. And in doing so, the star becomes fragile, unstable. Its surface is not uniform, but pocked with great cells of gas. Some astronomers believe a single one of these bubbles, convective cells, can be larger than Earth's entire orbit. At the center of this expanding colossus, fusion still occurs. Hydrogen has long been depleted, and helium is now fusing into heavier elements, carbon, oxygen, magnesium. This is a critical phase. The star is nearing its end. Once the core becomes too heavy to resist collapse, iron will form, and iron is the great boundary in stellar physics. Fusion of iron doesn't release energy, it absorbs it. When that moment comes, the balance shatters, and the star will implode. But that is still in the future. For now, Scuti pulses slowly, like a cosmic heartbeat. It is classified as a pulsating variable star, its brightness shifting as its outer layers expand and contract. This breathing cycle is slow, months long, and gives the star its rhythm, like the tide. From your vantage point, you observe another peculiarity. JWST is losing mass. Its outer layers drift away, carried off by stellar winds, streams of particles blown by radiation pressure. Over time, this process peels the star apart. It's one of the reasons astronomers debate its actual size. Because the outer envelope is so diffuse, it's hard to say where the star truly ends. You reflect for a moment on how little of this was known just decades ago. In the 20th century, red supergiants were assumed to be rare, mysterious anomalies. Only with the rise of space telescopes and precise spectroscopic methods did we begin to map their true dimensions. And even now, some data is debated. Distance estimates, mass loss rates, temperature fluctuations. But uncertainty doesn't dim the wonder, it expands it. Some researchers propose that JWST may shrink as it evolves, its mass loss and internal changes gradually collapsing it into a hotter, smaller star before the final supernova. Others believe it may be on the brink already, that its next contraction could be the last. The supernova of a star like this would not just be bright, it would be transformative, a release of energy so vast it could outshine an entire galaxy for weeks. Neutrinos would flood space. Elements like gold, platinum, and uranium would be born in that furnace. This is cosmic alchemy, stars turning themselves inside out to seed the universe with complexity. But tonight, that moment is not here yet. Tonight you float beside a star so large, your mind falters at the scale. The texture of it, the slowness of its surface, the quiet distance of its core. You feel as though you are orbiting a whole world, not a single star. And still, even in this enormity, JWST is not alone. Other giants await, some even larger, some far more massive. You begin to pull away, your thoughts still trailing behind. The red light lingers in your vision, like the afterglow of a dream. Ahead, space is darker again, but not empty. In the far silence, another giant pulses. This one, less known, more obscure, but perhaps even larger. Its name is whispered among catalogs and in quiet debates. Stephenson 2:18. You turn toward it, letting the light of JWST fade gently behind you, and begin the slow glide, deeper into the realm of hypergiants. You learn why some stars are larger, others heavier, and how this affects their fate. As you drift onward, the red glow of JWST dissolves behind you, like a sunset slipping below the edge of time. Ahead, space stretches wide and cool, a canvas of subtle light and gravitational tension. You move through stillness, but the physics beneath that stillness hums with complexity. Out here, size is not always what it seems. One star might swell to the edge of Saturn's orbit, yet possess only a fraction of the mass of another smaller, hotter star. In astronomy, the distinction between volume and mass becomes crucial. You let your thoughts wander through this quiet paradox. JWST, for example, is enormous in size, its radius vast, but its mass is relatively modest among giants, somewhere between 7 and 10 times that of our Sun. Compare that to a star like R136A1, which you will soon meet. That one is far smaller in diameter, but could contain nearly 200 or even 300 solar masses. It blazes with intensity, not through sheer size, but by its unimaginable density and fusion rate. Why is that? You consider the balance at the heart of every star, the push and pull of gravity and pressure. A massive star's gravity pulls everything inward, while fusion at the core pushes outward, releasing radiation. This balance defines the star's shape, size, temperature, and lifespan. The more massive a star is, the greater the pressure at its core. To maintain equilibrium, it must fuse elements more rapidly. That intense activity makes it brighter, but it also shortens its life. A giant like R136A1 might burn through its fuel in just a few million years. Meanwhile, a smaller star can shine calmly for tens or even hundreds of billions. Yet not all massive stars are large in radius. Many, like blue giants and Wolf-Rayet stars, are compact and hot. Their outer layers are stripped or compressed. Some, despite burning brightly, are barely 10 times larger than our Sun by radius. Nothing like the sprawling atmosphere of a red hypergiant. It's like comparing a bonfire to a smoldering ember the size of a mountain. Both burn, both glow, but one is intense, short-lived, the other diffuse and slow. This tension shapes every step of a star's life. Mass is also destiny. A star's mass determines what it becomes when it dies. If it begins with under 8 solar masses, it might swell into a red giant, and then settle quietly as a white dwarf, cooling slowly, over trillions of years. But if it starts with over 20 or 30 or more, its end is cataclysmic. A supernova, a neutron star, a black hole. There are thresholds, and you pass them silently as you drift. Somewhere behind you lies the boundary between stars that end quietly and those that collapse with violence. Somewhere ahead lies the limit where even neutron stars can't survive their own mass, and space folds inward. Some scientists propose more exotic ends, quark stars, for instance, hypothetical objects denser than neutron stars, but not quite black holes. In these stars, neutrons are squeezed so tightly that their constituent quarks may separate, forming a sea of strange matter. No such object has been confirmed yet, but the physics doesn't rule them out. Somewhere in the deep silence, perhaps one already exists. Back in your current path, mass continues to guide the stars you approach. The next behemoth, Stephenson 218, is an oddity. If estimates hold true, its volume exceeds even UY Scutis, and yet its mass, while substantial, is likely under 40 solar masses. It is wide, but not wildly heavy. A reminder that size does not equal strength. This behemoth likely belongs to a stellar association, a loose group of red supergiants known as Stephenson 2, or ST2, located around 19,000 light-years from Earth. The entire region glows in infrared, partially hidden behind a thick layer of interstellar dust. To see it, astronomers peer through long wavelengths, watching for thermal traces that shine. Like heat seen through fog, you reflect on how much of the universe is invisible, not because it's hidden maliciously, but because your human eyes are tuned to such a narrow band of light. Like listening to a song and hearing only one instrument. Fortunately, your thoughts have no such limits here. You float through X-ray bursts and infrared ribbons, through gravity waves and magnetic storms. Each layer of the universe adds another brushstroke to the vast, silent portrait. And as the shape of Stephenson 218 rises before you, still distant, still only a ghostly glow in the haze, you consider the quiet truth that space teaches best. That scale is not always power, that the universe is not arranged by what impresses the eye, but by what holds its balance. You drift slower now, as if nearing the edge of something sacred. You've learned how stars wear their size and mass like masks, some bright and dense, some vast and fading, and ahead, the deepest mask yet awaits. You approach a veiled red hypergiant, cloaked in interstellar dust, barely visible yet vast beyond measure. You pass through the last of the open void, entering a field of mottled shadows. The light here is soft, not because it isn't present, but because it is scattered and filtered by fine grains of interstellar dust. This is the domain of Stephenson 218, a red hypergiant so immense, it defies simple comparison. Its true nature is shrouded, not only in distance but in uncertainty. Even today, it exists in our data more as a probability than a fully resolved object. The veil around it is literal, thick with carbon-rich dust and cool gas, and figurative, in the sense that many of its measurements are inferred from indirect observations. Still, the picture that emerges is staggering. The star lies approximately 19,500 light-years from Earth, in the constellation Scutum, nestled within a massive cluster known as Stephenson 2, a cradle of red supergiants. But Stephenson 218 is not simply one of many. It may be the largest of all, with a radius potentially exceeding 2,100 times that of our Sun. To put that in perspective, if you replaced the Sun with Stephenson 218, its photosphere would reach well past Saturn and possibly graze the orbit of Uranus. You float slowly towards this diffuse colossus, and even now, you can't clearly define its surface. It is more atmosphere than object, more presence than point. Its outer layers are extremely tenuous, more like a fog than a skin. They drift, ripple, and escape into space. The density is so low, you could pass through the outer half of the star without ever feeling resistance, without even sensing that you were inside something at all. And yet, you drift through its outer envelope, immersed in a slow churning sea of heated gas. Here, temperatures are relatively cool, around 3,000 Kelvin, and the pressure is low, but deeper in the story changes. The further you go, the more intense the heat, the more violent the motion. Turbulence rises, the fusion furnace stirs. Stephenson 218 is thought to be near the end of its life. Like UI Scuti, it has exhausted the hydrogen in its core and is fusing heavier elements in successive shells. Each fusion layer is like a nesting doll. Hydrogen, helium, carbon, oxygen, each deeper, hotter, and shorter-lived. Eventually, as with all massive stars, it will build up an iron core, and when that happens, gravity will win. In a fraction of a second, the balance will collapse, the core will implode, and the outer layers will rebound in a supernova, an explosion that will send shockwaves through the surrounding dust and gas, igniting new stars in its wake. It is the ultimate punctuation mark to a stellar life, but sometimes something even more exotic occurs. If the collapsing core is massive enough, the pressure can go beyond neutron degeneracy, the point where even neutrons resist compression. Gravity wins entirely, space folds in on itself, and the result is a black hole, an object so dense, not even light can escape. It is the final victory of gravity, the quietest and most complete. You float away from this imagined core, back toward the outer layers. Here the gases are lighter, more diffuse. Solar winds blow steadily outward. In massive stars, these winds are intense, stripping away mass at phenomenal rates. Over millions of years, a star might lose half its mass or more before it ever explodes. In lower mass stars like our Sun, fusion will never reach iron. It will stop at helium and carbon, eventually ejecting the outer layers in a soft, glowing cloud, a planetary nebula, and leaving behind a white dwarf, a dense cinder slowly cooling in space. The diversity of stellar fates all stems from this balance, how long fusion holds gravity at bay. And yet, you realize, no star lasts forever. Fusion is a delay, not a solution, a beautiful pause in the collapse that shapes all matter. And without it, there would be no light, no warmth, no planets, no life. In this moment, you feel the deep humility of that truth. Everything you are, all your atoms, all your breath, was once held inside a star's fusion engine, cooked, balanced, released, and given to the galaxy. Somewhere, a new star is forming. Somewhere else, another is fading. And you are exactly where you are meant to be, between them, resting in the pause, the echo, the space between pulses. May the silence of the cosmos cradle you. May the memory of the stars wrap you, and may the slow rhythm of drifting carry you into deep, unbroken sleep. Good night, traveler. Sleep well. Sleep wide. A star that's died, yet its power makes the universe tremble. Neutron stars, where matter is crushed to the extreme and the impossible becomes reality. Imagine staring into a cosmic void where a faint, rhythmic pulse of light flickers like a heartbeat from an unseen star. What could forge such a relentless, radiant pulse, defying the silence of space? Welcome to the enigma of neutron stars, the pulsing hearts of the cosmos, where the ashes of colossal stars beat with a ferocity that reshapes our understanding of reality. These celestial relics born from cataclysmic explosions pack the mass of our sun into a sphere no wider than a city, spinning with a rhythm that echoes across light years. Far beyond what school textbooks taught, neutron stars challenge our grasp of physics, time, and existence itself, inviting us to peer into a universe both alien and awe-inspiring. Neutron stars are not just astronomical curiosities. They are cosmic laboratories where the laws of nature are stretched to their limits. Picture the heart of a supernova, where a dying star collapses, crushing its core into a dense, spinning orb that pulses with energy. This is no ordinary star, but a neutron star, a celestial marvel with a density so extreme that a single teaspoon of its material would weigh as much as Mount Everest. Its surface, smoother than glass, hides a core where matter may dissolve into strange, exotic forms. These stars don't merely shine. They broadcast their presence through beams of radiation, like a lighthouse sweeping the cosmos detected here on Earth as rhythmic pulses. Why do these pulses captivate us? Because they whisper secrets of the universe's most extreme conditions, encoded in a heartbeat that has traveled millions of years to reach our telescopes. This journey into neutron stars is a voyage through time and thought, one that will unravel mysteries school never touched. We'll begin by tracing the historical quest to understand these cosmic hearts, from ancient stargazers who glimpsed their explosive births to the scientists who decoded their rhythmic signals. Then we'll dive into the science of their extraordinary nature, how their immense gravity warps time, how their magnetic fields rival 1 trillion refrigerator magnets, and how they forge the gold in your jewelry. We'll explore modern discoveries from waves rippling through space-time to theories of alien matter lurking in their cores. Finally, we'll reflect on what these pulsing hearts reveal about our place in the vast interconnected cosmos. The neutron star's heartbeat is more than a signal. It's a mirror reflecting the universe's deepest truths. But why should we care about a star so distant, so strange? Neutron stars are not just relics. They are keys to unlocking questions that haunt us. How do stars die, and what do their deaths create? Can matter exist in forms we can't imagine? Might these cosmic hearts hold clues to the universe's origin, or its ultimate fate? As we stand on Earth, gazing at their faint pulses, we're not just observing. We're connecting with a force that shapes reality itself. The neutron star's pulse is a call to wonder, a reminder that the universe is alive with mysteries waiting to be explored. So let's follow this heartbeat, this radiant rhythm, and discover what lies beyond the lessons of school, deep within the pulsing heart of the cosmos. Long before telescopes pierced the heavens, ancient stargazers stood beneath a glittering sky, their eyes catching fleeting bursts of light from distant cataclysms. Could they have imagined that these fiery spectacles were the birth cries of neutron stars, the pulsing hearts of the cosmos? Thousands of years ago, in 1054, Chinese astronomers recorded a guest star blazing in the constellation Taurus, so bright it shone in daylight for weeks. Unknown to them, this was the Crab Nebula's supernova, a stellar explosion forging a neutron star whose heartbeat we still detect today. This cosmic pulse, a rhythm of radiant energy, has echoed through history, guiding curious minds to unravel a mystery schoolbooks barely touched. Let's journey through time tracing how humanity first heard the universe's pulse and began to understand its profound significance. In the 18th century, as astronomers mapped the stars, an English cleric named John Michell pondered a radical idea. What if a star's gravity was so immense that even light couldn't escape? His dark stars were a faint whisper of neutron stars too strange for his era to grasp. Fast forward to the 1930s, when Fritz Zwicky and Walter Bade, gazing at the cosmos, proposed that supernovae left behind dense cores. They called these neutron stars imagining a stellar corpse, where matter was crushed into a near-infinite density. Their vision was like tuning a radio to catch the faint pulse of a cosmic heart, a signal too weak for the technology of their time. Yet their bold hypothesis set the stage for a discovery that would shake the foundations of astronomy. In 1967, a young graduate student, Jocelyn Bell Burnell, sat hunched over a radio telescope in Cambridge, England, sifting through reams of data. Amid the static, she noticed a peculiar regular blip every 1.33 seconds, as precise as a metronome. At first, her team dubbed it LGM-1, half joking that it might be a signal from little green men. But this was no alien broadcast. It was the pulse of a neutron star, a pulsar spinning furiously and beaming radio waves like a cosmic lighthouse. Bell Burnell's discovery was a triumph, revealing the neutron star's heartbeat to the world. The Crab pulsar, that ancient guest star of 1054, was among the first confirmed its rapid pulse, a testament to a star's violent end. Her work, though initially overlooked for a Nobel Prize, ignited a new era of cosmic exploration. These historical milestones, from ancient skywatchers to Bell Burnell's breakthrough, are like reflections in the cosmic mirror, each catching a glimpse of the neutron star's pulsing heart. They show humanity's relentless drive to decode the universe's signals, even when the tools were crude or the ideas outlandish. Michel's dark stars, Zwicky's dense cores, and Bell Burnell's blips were steps toward understanding a celestial enigma. Neutron stars, with their relentless rhythms, weren't just theoretical curiosities. They were real, their pulses a drumbeat echoing across the cosmos. As we move forward, we'll delve into the science behind these extraordinary objects, exploring how their heartbeat shapes the universe and what secrets it holds for us today. Picture a city-sized sphere spinning hundreds of times per second, its surface pulsing like the relentless beat of a cosmic heart. How can a neutron star, this pulsing heart of the cosmos, defy our everyday understanding of matter and time? These stellar remnants are not just dead stars. They are extreme laboratories where gravity, magnetism, and quantum forces collide in ways schoolbooks never dared to explore. Born from the fiery collapse of massive stars, neutron stars pack the sun's mass into a ball just 20 kilometers wide, creating densities so immense that a single sugar cube of their material would outweigh Earth's entire population. Let's unravel the science behind their extraordinary nature, from their crushing gravity to their role as cosmic alchemists forging the universe's heaviest elements. Imagine squeezing an ocean liner into a thimble that's the density of a neutron star. Its core, crushed by unimaginable pressure, may transform into exotic matter, perhaps a soup of quarks, unbound from normal atoms. This density warps space-time, bending light and slowing time itself. If you stood on a neutron star's surface, an impossible feat, your watch would tick slower than on Earth, a quirk of Einstein's relativity called time dilation. A minute there might feel like hours to a distant observer, as if the cosmic heart's pulse stretches the fabric of reality. This gravity is so fierce that mountains on a neutron star's surface, smoother than a billiard ball, are mere millimeters tall, flattened by the star's own weight. Yet this compact orb spins with dizzying speed, some pulsars whirling 700 times per second, faster than a kitchen blender, sending beams of radiation sweeping across space like a lighthouse's glow. These beams are powered by magnetic fields 1 trillion times stronger than Earth's fields, so intense they could rip apart a spaceship. When a neutron star's magnetic poles misalign with its spin, it emits radio waves, X-rays, or gamma rays, creating the pulses Jocelyn Bell Burnell detected. These pulsars are cosmic clocks, their beats so precise they rival atomic clocks, allowing astronomers to map the galaxy or test relativity. But neutron stars do more than pulse. They forge elements like gold and silver. During a supernova, rapid neutron capture creates heavy elements, and when two neutron stars collide, as seen in 2017's gravitational wave event, they spew these treasures into space. Picture the cosmic heart pumping, not blood, but the raw materials of planets and jewelry, a celestial forge shaping the universe's wealth. Beneath their surface, neutron stars hide mysteries. Their cores may host strange states of matter, like quark-gluon plasma, where protons and neutrons dissolve. Some theories suggest superfluids flow without friction, creating a frictionless dance within the star's heart. These conditions push physics to its limits, challenging our understanding of quantum mechanics. Neutron stars are also cosmic dynamos, their spins generating energy that outshines the sun for millennia. As we'll see next, modern discoveries are peeling back these layers, revealing how these pulsing hearts ripple space-time and hint at the universe's deepest secrets, all encoded in their relentless radiant beat. What secrets does the pulsing heart of the cosmos whisper to us today as its radiant beats ripple through modern telescopes? Neutron stars, those city-sized relics of stellar explosions, are no longer just distant curiosities. They're cosmic beacons, illuminating the universe's deepest mysteries. In recent years, astronomers have caught their pulses in unprecedented detail, from gravitational waves born of their collisions to strange matter lurking in their cores. These discoveries, far beyond schoolroom lessons, reveal neutron stars as keys to understanding matter spacetime and even our technological future. Let's explore how the relentless heartbeat of these stars echoes through cutting-edge science, reshaping our view of the cosmos and sparking questions about what lies ahead. In 2017, a cosmic symphony reached Earth, detected by the Laser Interferometer Gravitational Wave Observatory, or LIGO. Two neutron stars locked in a death spiral collided 130 million light-years away, sending ripples through space-time. This event, named JW170817, was a milestone confirming that neutron star mergers forge heavy elements like gold and uranium as their pulsing hearts pump out a cosmic furnace. Telescopes caught the afterglow, a dazzling burst of light, proving these collisions light up the universe. Unlike black holes, neutron stars leave visible scars, their radiant pulses offering a window into gravity's extreme dance. This discovery linked the cosmic heart's beat to the creation of the very atoms in our world, suggesting that the jewelry on your finger owes its existence to such cataclysmic embraces. But what lies within a neutron star's core? Modern theories propose exotic states of matter, like quark-gluon plasma, where protons and neutrons dissolve into a primordial soup. Imagine the cosmic heart compressing matter so fiercely that it mimics the universe's state just after the Big Bang. Experiments like those at CERN's Large Hadron Collider aim to replicate these conditions, but neutron stars are natural laboratories, their pulses encoding clues about physics beyond our reach. Some suggest superfluids swirl in their cores, flowing without friction, while others hypothesize strange quark matter, a stable state denser than nuclear matter. These ideas push quantum mechanics to its limits, with each pulse of the cosmic heart offering a testbed for theories that could rewrite our understanding of reality. Neutron stars also inspire technological dreams. Their precise pulses, rivaling atomic clocks, could guide interstellar navigation, acting as cosmic lighthouses for future spacecraft. Magnetar's neutron stars with ultra-strong magnetic fields hint at energy sources dwarfing nuclear power, sparking ideas for harnessing their radiant energy. Philosophically, neutron stars challenge us if their cores hold alien matter. What does this mean for our place in the cosmos? Are we like their pulses, fleeting signals in an infinite universe? Imagine yourself drifting silently in the vastness of space. Before you, a galaxy spins a luminous whirlpool of billions of stars, gas and dust. The core glows brilliantly, surrounded by spiraling arms stretching out like cosmic ribbons. It's a mesmerizing dance of light and motion held together by a gravitational force so immense it defies comprehension. Yet hidden within this stunning spectacle is an enigma. The visible elements of the galaxy, stars, planets, and nebulae account for only a fraction of the mass needed to sustain this intricate ballet. What is holding these celestial bodies together? What invisible force anchors the galaxy's swirling arms, ensuring it doesn't fly apart? This is the mystery of dark matter, the unseen framework of the universe. It doesn't emit light or energy, making it undetectable by traditional telescopes. Yet its gravitational pull shapes galaxies, clusters, and the universe itself. It is the scaffolding upon which the cosmos is built. The idea of dark matter arose when astronomers noticed discrepancies between what they could see and the behavior of galaxies. In the 1930s, Fritz Zwicky, a Swiss astrophysicist, observed that galaxies in the Coma cluster were moving faster than expected. By applying Newtonian physics, he calculated that visible matter alone couldn't generate enough gravity to hold the cluster together. There had to be some missing mass providing the necessary gravitational glue. Decades later, Vera Rubin and Kent Ford confirmed this phenomenon within individual galaxies. Studying the rotation curves of spiral galaxies, they discovered something astonishing. Stars on the outer edges of galaxies were moving just as fast as those near the center. According to the laws of gravity, this was impossible unless there was an unseen mass extending far beyond the visible boundaries. This realization that most of the universe's mass is invisible reshaped our understanding of the cosmos. Today, scientists estimate that dark matter constitutes roughly 27% of the universe, dwarfing the mere 5% made up of ordinary matter. The rest, even more mysterious, is dark energy. The invisibility of dark matter sets the stage for one of science's greatest pursuits. It's a riddle that challenges the boundaries of our knowledge, compelling us to peer deeper into the fabric of reality. What is this unseen force? How does it interact with the visible universe? And what does its existence mean for our understanding of life? Existence and everything in between. The hunt for dark matter isn't just about solving an abstract puzzle. It's about uncovering the fundamental truths of the universe. If we can understand this invisible force, we might unlock secrets about how galaxies form, why the universe expands as it does, and perhaps even glimpse the forces that shaped the cosmos in its infancy. This is the unseen force shaping our universe. It surrounds us, permeates us, and holds the cosmos together. To understand dark matter is to understand the universe itself. And so the quest begins with questions as vast and profound as the galaxies swirling in the night sky. To uncover the presence of something unseen, scientists rely on the subtle traces it leaves behind. One of the most compelling pieces of indirect evidence for dark matter comes from the phenomenon of gravitational lensing, a striking consequence of Einstein's theory of general relativity. Gravitational lensing occurs when the gravity of a massive object, like a galaxy or cluster of galaxies, bends the path of light from a more distant source. This bending creates distorted, magnified, or even multiple images of the background object, much like a glass lens does. When astronomers measure the extent of this lensing, they find something peculiar. The visible mass of the galaxy or cluster is far too small to account for the degree of light bending. The gravitational pull needed to create these effects is immense, far greater than what observable matter could produce. This discrepancy points to the presence of an unseen mass surrounding and permeating these galaxies. Dark matter, though invisible, exerts a gravitational influence that reveals itself through these cosmic distortions, allowing astronomers to see its effects, even if they can't directly observe the matter itself. Another key piece of evidence for dark matter comes from the rotation curves of galaxies. Graphs showing the velocity of stars and gas as a function of their distance from the galactic center. In a galaxy governed solely by the visible matter, you'd expect the stars further from the center to orbit more slowly, similar to how planets in our solar system move. This is because gravity weakens with distance, and the mass producing the gravitational pull would primarily reside in the dense star-filled core. However, observations tell a very different story. When Vera Rubin and her colleagues measured the rotation speeds of stars in spiral galaxies, they found that these velocities remain nearly constant, even at great distances from the galactic center. This flat rotation curve implies the existence of a vast, unseen halo of mass, extending far beyond the visible stars. Without this invisible matter, the stars at the outskirts of the galaxy should be flung off into space, unable to maintain their high velocities. The logical conclusion: a massive halo of dark matter envelops the galaxy, providing the necessary gravitational pull to stabilize the outer stars. Gravitational lensing and galaxy rotation curves are two sides of the same coin, each offering a glimpse of dark matter's pervasive role in the universe. Together they form a consistent narrative. There is far more to the cosmos than meets the eye. Dark matter doesn't just shape individual galaxies, it influences entire clusters. In fact, gravitational lensing studies of massive galaxy clusters reveal intricate maps of dark matter's distribution, showing how it congregates in enormous structures that act as the scaffolding of the universe. These clusters themselves are stabilized by dark matter's immense gravitational influence, just as individual galaxies are. These indirect observations highlight the ingenuity of science. Without the ability to see or directly interact with dark matter, researchers rely on its gravitational footprints to trace its existence. Each distorted image and unexpected star velocity is a clue bringing us closer to understanding the unseen. While the nature of dark matter remains elusive, these pieces of evidence confirm its presence beyond reasonable doubt. Dark matter is not a theoretical abstraction. It is a tangible force shaping the universe. Its detection may be indirect, but its impact on the cosmos is undeniable. Dark matter is enigmatic, not just because it's invisible to the naked eye, but because it interacts so weakly, if at all, with ordinary matter. This makes its direct detection an extraordinary challenge, requiring experiments of unparalleled sensitivity and precision. Despite these hurdles, scientists have devised ingenious methods and cutting-edge facilities to attempt what might seem impossible, capturing evidence of dark matter directly. The Large Hadron Collider, smashing particles to unveil mysteries. The Large Hadron Collider, LHC, located at CERN in Geneva, is the world's most powerful particle accelerator. With its 27-kilometer ring buried underground, the LHC smashes protons together at nearly the speed of light, creating conditions similar to those that existed moments after the Big Bang. These high-energy collisions produce a cascade of particles, which are meticulously analyzed by detectors to search for anomalies, potential fingerprints of dark matter. Scientists at the LHC are particularly interested in detecting WIMPs, weakly interacting massive particles, a leading candidate for dark matter. The theory suggests that WIMPs might be created during these collisions. If WIMPs exist, they could appear as missing energy in the data escaping the detectors, without interacting much like neutrinos. While no conclusive evidence for dark matter has yet emerged from the LHC, the experiments have provided valuable constraints, narrowing the range of possible properties that dark matter could possess. The search continues with upgraded detectors and refined collision parameters as researchers hope to one day spot dark matter particles among the debris of their high-energy collisions. Deep underground, shielded from cosmic rays and other background noise, lies the large underground xenon LUX detector, one of the most sensitive instruments ever built to hunt for dark matter. Located in the Sanford Underground Research Facility in South Dakota. LUX relies on a tank filled with ultra-pure liquid xenon to detect the faintest interactions between dark matter particles and normal matter. The principle is straightforward but ambitious. If a dark matter particle passes through the detector and collides with a xenon nucleus, it will produce a minuscule flash of light scintillation and a small ionization signal. These signals are then captured by ultra-sensitive photomultiplier tubes capable of detecting even the faintest whispers of activity. Although LUX has not yet observed definitive evidence of dark matter, its results have set new benchmarks for sensitivity, helping to rule out certain theoretical models. Its successor, LUX Zeppelin LZ, is even more advanced with a larger detector and enhanced capabilities to sift through the cosmic silence in search of dark matter's elusive presence. Beyond the LHC and LUX, numerous other experiments contribute to the hunt for dark matter. Projects like Xenon 1T in Italy, PICO in Canada, and Super CDMS in the United States employ different approaches from cryogenic detectors to bubble chambers to maximize the chances of detection. Each of these experiments tackles a specific aspect of the dark matter puzzle, reflecting the global collaboration and interdisciplinary innovation required to confront this profound challenge. The diversity of techniques ensures that even if one method fails, others may succeed in uncovering dark matter's secrets. The direct detection of dark matter would mark a watershed moment in physics, confirming the existence of a previously invisible component of the universe. It would provide not only answers to long-standing questions, but also open doors to entirely new realms of understanding. For now, the search continues, a testament to humanity's unyielding curiosity and determination to reveal the unseen forces shaping the cosmos. Detecting dark matter is one of the greatest challenges in modern physics. By its very nature, dark matter defies direct observation. It does not emit, absorb, or reflect light, nor does it interact with electromagnetic forces. Its presence can only be inferred through its gravitational effects, making the search akin to hunting shadows in a darkened room. Yet these obstacles have not deterred scientists. Instead, they have fueled ingenuity, pushing the boundaries of technology and theoretical physics. The prevailing hypothesis suggests that dark matter interacts only through gravity and possibly the weak nuclear force. If true, this means that dark matter particles pass through ordinary matter almost entirely unnoticed. For context, billions of dark matter particles could be streaming through your body at this very moment, leaving no trace of their passage. This weak interaction necessitates detectors of extraordinary sensitivity. These instruments must distinguish potential dark matter signals from a cacophony of background noise, including cosmic rays, neutrinos, and even natural radioactivity in the Earth itself. To overcome this, experiments are often placed deep underground or in remote locations to minimize interference. The pursuit of dark matter demands cutting-edge technology, which comes with significant costs. Facilities like the Large Hadron Collider and underground detectors like LUX or Xenon require immense financial and logistical support. Furthermore, the sheer complexity of these instruments means that even minor malfunctions can delay research for months or years. For instance, Liquid xenon detectors must maintain extreme purity to avoid contamination that could mimic dark matter interactions. Achieving this level of precision requires meticulous engineering and constant monitoring, making every experiment a balancing act between innovation and practicality. One of the greatest challenges in the hunt for dark matter is the uncertainty surrounding its nature. While theories like WIMPs, weakly interacting massive particles, dominate the conversation, other candidates such as axions, sterile neutrinos, and primordial black holes offer competing possibilities. Each theory demands a different experimental approach, dividing resources and efforts. Moreover, if dark matter does not conform to these existing models, scientists may be searching in the wrong direction entirely. The possibility that dark matter interacts via unknown forces or consists of particles beyond the standard model of physics remains an ever-present challenge, forcing researchers to constantly reevaluate their assumptions. Dark matter is not evenly distributed throughout the universe. It clusters in halos around galaxies and galaxy clusters, but its density varies significantly depending on location. Detecting dark matter on Earth might therefore be akin to searching for a single grain of sand in an entire desert, a problem of scale and probability. This uneven distribution also complicates experimental timing. Certain experiments rely on the Earth's motion through the galaxy to detect variations in dark matter, particle flux. Such seasonal or directional signals are faint and require years of data collection to confirm. Despite these formidable challenges, the search for dark matter continues with unwavering determination. Each failed experiment provides critical data, narrowing the field of possibilities and refining our understanding. These incremental advances are essential steps in the scientific process, building toward an eventual breakthrough. The global effort to detect dark matter involves thousands of researchers, engineers, and theorists working collaboratively across disciplines. New experiments like the upcoming Lux-Zeppelin LZ detector and advancements in neutrino observatories are poised to push the limits of sensitivity even further. Theoretical physicists, meanwhile, continue to develop models that integrate dark matter into the broader framework of cosmic evolution, offering fresh perspectives and potential avenues for detection. The stakes are high. Detecting dark matter would not only confirm its existence, but also revolutionize our understanding of the universe. It could illuminate the processes that shaped galaxies, provide insights into the early moments of the cosmos, and reveal connections between the macroscopic structure of the universe and the microscopic world of particles. Above all, the pursuit of dark matter represents the essence of human curiosity. It is a testament to our drive to understand the unseen, to uncover the forces that bind the cosmos together, and to push beyond the boundaries of what is known. The standard model of particle physics is one of the most successful theories in science. It describes the fundamental particles, quarks, leptons, and bosons, and the forces that govern their interactions. The electromagnetic weak and strong nuclear forces. With the discovery of the Higgs boson in 2012, the standard model seemed complete, offering a coherent explanation for much of the observable universe. However, there's one glaring problem: the standard model doesn't account for dark matter. While it elegantly explains the behavior of ordinary matter, it fails to include the mysterious substance that constitutes roughly 27% of the universe's mass-energy content. This discrepancy has placed the standard model under immense strain, compelling scientists to search for extensions or entirely new frameworks. One of the clearest ways dark matter challenges particle physics is through its gravitational effects. The standard model has no particle capable of producing the massive gravitational influence attributed to dark matter. Neutrinos, the only standard model particles that interact weakly and are electrically neutral, were once considered candidates. However, their tiny masses and high velocities render them incapable of explaining the observed behavior of galaxies and galaxy clusters. Dark matter's gravitational effects indicate it must consist of a new type of particle, one that interacts weakly with ordinary matter, but has sufficient mass to shape the cosmos. This requirement forces researchers to look beyond the standard model for answers. Dark matter's invisibility stems from its apparent lack of interaction with electromagnetic forces. It does not emit, absorb, or reflect light, making it undetectable through traditional methods. This property places it outside the realm of particles, like electrons or photons, which are central to the standard model. The absence of electromagnetic interaction raises profound questions about the nature of dark matter. Does it belong to an entirely new class of particles? Does it interact via unknown forces? These possibilities hint at physics beyond the established paradigm, requiring theoretical innovation. Dark matter's existence suggests that the standard model is incomplete. Several theories aim to bridge this gap, including supersymmetry, SUSY. This theoretical framework extends the standard model by proposing a partner particle for each known particle. In this context, the lightest supersymmetric particle, LSP, such as a neutralino, is a promising dark matter candidate. However, the failure of experiments like the Large Hadron Collider to detect supersymmetric particles has cast doubt on this theory. Hidden sectors. Some models propose that dark matter resides in a hidden sector, a parallel universe of particles and forces that interacts with ordinary matter only through gravity or other weak interactions. This idea introduces exotic particles like axions and sterile neutrinos as potential dark matter candidates. Modified gravity. While not a particle-based solution, some physicists explore the idea that our understanding of gravity itself may be incomplete. Theories like modified Newtonian dynamics, MOND, challenge the need for dark matter by suggesting that gravity behaves differently on cosmic scales. However, these theories struggle to match the evidence provided by phenomena like gravitational lensing. Dark matter doesn't just challenge the standard model, it opens a window into uncharted territory. If dark matter particles are discovered, they could revolutionize our understanding of the universe's evolution, the forces that govern it, and the underlying structure of reality itself. Such a breakthrough might unify disparate areas of physics from the quantum scale to cosmological structures, offering insights into long-standing mysteries like the nature of gravity and the origins of the universe. Among the myriad theories proposed to explain dark matter, WIMPs, or weakly interacting massive particles, stand as the frontrunners. WIMPs are hypothetical particles predicted to have masses much greater than that of protons, yet they interact only weakly with ordinary matter. This means they can pass through stars, planets, and even our bodies without leaving a trace. The appeal of WIMPs lies in their compatibility with the thermal relic hypothesis. In the early universe, particles were created and annihilated in high-energy interactions. As the universe expanded and cooled, most of these particles decayed or annihilated, but some remained. The predicted abundance of WIMPs aligns closely with the observed density of dark matter, making them a compelling candidate. Another promising dark matter candidate is the axion, a hypothetical particle much lighter than WIMPs. Axions arise from solutions to theoretical problems in the standard model, specifically the strong CP problem, which involves the behavior of quarks and gluons in quantum chromodynamics. QCD, unlike WIMPs, axions are extraordinarily light and interact extremely weakly with both matter and radiation. What makes axions fascinating is their potential to form a vast invisible field permeating the universe. These particles could also account for the observed rotation curves of galaxies and other gravitational phenomena attributed to dark matter. Ongoing experiments such as the Axion Dark Matter Experiment, ADMX, aim to detect axions by searching for their predicted interaction with electromagnetic fields. Sterile neutrinos, a shadowy variant. Sterile neutrinos are an extension of the Standard Model's neutrinos, but differ in a crucial way. They do not interact via any of the known forces except gravity. These heavier, sterile counterparts of regular neutrinos could constitute dark matter if they were produced in sufficient abundance in the early universe. Sterile neutrinos are intriguing because their decay could emit detectable X-rays. Observations of unexplained X-ray emissions from galaxies and galaxy clusters have fueled interest in this candidate, though no definitive evidence has yet emerged. Primordial black holes, dark matter without particles. A more unconventional candidate for dark matter is primordial black holes, PBHs. Unlike particle-based explanations, PBHs are compact objects that might have formed shortly after the Big Bang. These black holes could range in size from microscopic to many times the mass of the Sun, and might account for at least part of the universe's dark matter. Although PBHs do not require exotic new particles, their presence would profoundly impact our understanding of cosmology and the early universe. Studies of gravitational lensing and cosmic background radiation are ongoing to determine whether PBHs could explain the observed effects of dark matter. The diversity of dark matter candidates reflects the breadth of the challenge. Beyond WIMPs, axions, sterile neutrinos, and primordial black holes, researchers explore other possibilities, including superfluid dark matter, a theory suggesting that dark matter could form a quantum superfluid, influencing gravity in unique ways. Fuzzy dark matter, extremely light particles with wave-like properties that could form large-scale structures. Self-interacting dark matter, particles that interact with themselves but not with ordinary matter, potentially explaining certain galactic phenomena. Each candidate represents a different facet of the dark matter puzzle. WIMPs dominate collider and underground detection efforts, while axions and sterile neutrinos push the boundaries of particle physics. Primordial black holes and exotic theories challenge the very concept of what dark matter might be. The search for these candidates is a testament to the creativity and adaptability of science. Whether dark matter turns out to be a familiar particle or something entirely unexpected, its discovery will revolutionize our understanding of the cosmos and the laws that govern it. The discovery of dark matter would revolutionize our understanding of the universe's history and structure. Currently, dark matter is considered the invisible scaffolding upon which galaxies and larger cosmic structures are built. By unraveling its nature, we could answer fundamental questions about how the universe formed, evolved, and reached its present state. In the early universe, shortly after the Big Bang, dark matter played a crucial role in shaping the cosmic web. While ordinary matter interacted with light and radiation, dark matter remained unaffected by electromagnetic forces, allowing it to clump together under gravity. These clumps served as gravitational wells, pulling ordinary matter into them and forming the seeds of galaxies. Discovering the properties of dark matter would refine our models of these early processes, offering a clearer picture of how galaxies, stars, and planets emerged. The universe is structured in a vast, interconnected web of galaxies, clusters, and voids. This cosmic web is shaped by the gravitational influence of dark matter. Without it, these structures would not exist as we observe them today. If dark matter's properties were identified, such as its mass interaction strength or particle behavior, scientists could better simulate the universe's large-scale evolution. These insights would bridge gaps in our understanding of how cosmic structures formed over billions of years and how they continue to evolve under the influence of both dark matter and dark energy. Dark matter's role isn't limited to the past. It also shapes the future. The gravitational pull of dark matter counters the expansive force of dark energy, which drives the acceleration of the universe's expansion. Understanding the balance between these forces could help predict the ultimate fate of the cosmos. If dark matter interacts in ways we don't yet understand, it could influence whether the universe continues expanding forever, eventually freezing in a heat death, or contracts in a big crunch. Alternatively, if dark matter decays over cosmic timescales, its diminishing influence could allow dark energy to dominate, leading to even more rapid acceleration and a big rip. By identifying and studying dark matter, physicists could refine these scenarios, offering profound insights into the universe's destiny. Dark matter discovery would unify two seemingly disparate realms of physics, the quantum and the cosmic. At its core, dark matter likely consists of particles governed by quantum mechanics, yet its influence is felt on the largest scales, shaping galaxies and the universe itself. This connection might lead to breakthroughs in other areas of science, such as particle physics. Discovering dark matter, particles could expose new forces or symmetries in nature, leading to extensions of the Standard Model. Astrophysics understanding dark matter would refine models of star formation, galaxy dynamics, and black hole behavior. Cosmology insights into dark matter could provide clues about the universe's earliest moments, potentially shedding light on inflation or other processes near the Big Bang. Beyond the scientific implications, discovering dark matter would profoundly impact how humanity views its place in the cosmos. It would reveal that much of the universe consists of something fundamentally different from the matter that makes up our bodies, our planet, and everything we've ever known. This realization could deepen our sense of connection to the cosmos, emphasizing that we are part of a much larger, more mysterious whole. Perhaps the most exciting implication of discovering dark matter lies in the doors it could open. Historically, every major scientific breakthrough has led to unexpected discoveries. Electricity paved the way for modern technology, and quantum mechanics revolutionized our understanding of the universe. Similarly, understanding dark matter might reveal entirely new realms of physics forces or phenomena that we cannot yet imagine. In this sense, the discovery of dark matter is not just about solving a mystery. It's about expanding the boundaries of human knowledge, venturing into the unknown, and uncovering truths that could redefine our understanding of existence itself. Dark matter plays a fundamental role in cosmology, the study of the origin, evolution, and structure of the universe. Its gravitational influence serves as the backbone of cosmic structures, dictating how galaxies form, cluster, and evolve over billions of years. Without dark matter, the cosmos as we know it would not exist. Understanding dark matter is therefore essential to refining our models of the universe's formation and its large-scale behavior. In the early universe, just after the Big Bang, dark matter began to clump together under gravity, forming dense regions that acted as seeds for galaxy formation. Ordinary matter composed of atoms was initially scattered by intense radiation, but eventually fell into these dark matter wells, creating the galaxies and clusters we see today. Without dark matter, this process would have been impossibly slow, leaving a universe largely devoid of structure. Exploring dark matter is key to unraveling these early cosmic events. The universe is expanding, a fact first discovered by Edwin Hubble in the 1920s. Over time, this expansion has been found to be accelerating, driven by a mysterious force called dark energy. Dark matter and dark energy together dominate the universe, comprising approximately 95% of its total mass energy content. Their interplay shapes the dynamics of the cosmos. Dark matter slows the expansion through its gravitational pull, while dark energy pushes against it, driving acceleration. Understanding dark matter is critical to deciphering this delicate balance. The tug of war, how dark matter and dark energy interact, influences the rate of cosmic expansion. precise knowledge of dark matter's properties, its density distribution and interactions would allow cosmologists to make more accurate predictions about the universe's future trajectory. The ultimate fate of the universe. Whether the cosmos ends in a big freeze, big crunch, or big rip depends largely on the role and behavior of dark matter over cosmic timescales. The lambda cold dark matter is the prevailing framework in cosmology. It describes a universe composed of dark energy, dark matter, and ordinary matter. While lambda cold dark matter has been extraordinarily successful in explaining observations like the cosmic microwave background, radiation, and large-scale galaxy distributions, it remains incomplete without a deeper understanding of dark matter. Structure formation. Simulations of galaxy and cluster formation depend heavily on assumptions about dark matter's properties. Better understanding could resolve discrepancies between observed and simulated galaxy distributions, small-scale anomalies. The lambda cold dark matter model struggles to explain certain small-scale phenomena like the observed density profiles of dark matter in galaxies. The cusp core problem. A deeper understanding of dark matter could address these inconsistencies. Studying dark matter may also provide insights into the universe's infancy. Shortly after the Big Bang, conditions were so extreme that matter and energy were indistinguishable. Dark matter's behavior during this epoch could reveal clues about the inflationary era, the rapid expansion of the universe immediately following the Big Bang. Baryogenesis, the process by which ordinary matter came to dominate over antimatter. Rionization, the period when the first stars and galaxies began to form. Reionizing the universe's neutral hydrogen. By connecting the properties of dark matter to these events, cosmologists could fill gaps in our understanding of the universe's earliest moments. Dark matter research also has profound implications for understanding dark energy, the force driving cosmic acceleration. While these two phenomena are distinct, they are deeply intertwined in shaping the universe's fate. Studying dark matter may reveal new physics that unifies them, providing a more complete picture of the universe's mass energy content and its ultimate destiny. Understanding dark matter would mark a paradigm shift in cosmology, akin to Copernicus' heliocentric model or Einstein's theory of general relativity. It would not only refine our knowledge of the universe's expansion, but also reveal the fundamental processes that govern the cosmos. By answering the question of dark matter, we edge closer to answering the larger questions. Where did we come from? Where are we going? And what is the true nature of reality? The discovery of dark matter would be a watershed moment for particle physics, opening a door to realms of knowledge far beyond the Standard Model. While the Standard Model has been remarkably successful in describing the known particles and forces, it cannot account for the mysterious substance that makes up 27% of the universe. This glaring gap suggests the existence of entirely new particles forces or symmetries that extend the boundaries of our current understanding. If dark matter is composed of particles, discovering its true nature could revolutionize our understanding of the subatomic world. Among the most promising avenues are WIMPs, weakly interacting massive particles. As leading candidates, WIMPs would represent a new class of particles interacting via weak nuclear forces. Their discovery could reveal new interactions and extensions to the Standard Model, such as supersymmetry, which posits the existence of partner particles for all known particles. Axions. The discovery of axions would solve not only the dark matter mystery, but also the strong CP problem in quantum chromodynamics. Axions could provide a bridge between particle physics and cosmology, unveiling connections previously thought unrelated. Sterile neutrinos. These hypothetical particles, unlike their Standard Model counterparts, would only interact through gravity. Detecting sterile neutrinos could expand our knowledge of neutrino physics and offer insights into the behavior of other elusive particles. Each of these particles represents a possible paradigm shift, revealing interactions or dimensions of nature that are currently hidden from view. Dark matter could point to the existence of previously unknown forces or interactions. For example, dark sector physics. Some theories propose that dark matter interacts with itself through dark forces mediated by particles analogous to photons in the visible universe. Detecting these forces could unveil an entirely new layer of reality, a dark sector that exists parallel to our observable universe. Fifth, force of nature. If dark matter interacts with ordinary matter in unexpected ways, it might hint at a new fundamental force beyond the four currently known: gravitational, electromagnetic, strong nuclear, and weak nuclear forces. These discoveries would fundamentally alter our understanding of how the universe operates, potentially unifying disparate phenomena under a broader theoretical framework. One of the most profound implications of dark matter research lies in its potential to connect quantum mechanics and general relativity. Two pillars of modern physics that remain theoretically incompatible. Dark matter operates on both quantum and cosmic scales, offering a rare opportunity to study phenomena that could unify these frameworks. If dark matter consists of quantum particles with wave-like properties, its behavior might illuminate how quantum effects manifest on macroscopic gravitational scales. Understanding dark matter's gravitational effects could provide insights into quantum gravity, bringing us closer to a theory of everything. The hunt for dark matter has driven advancements in technology that benefit particle physics more broadly. High-energy experiments like those at the Large Hadron Collider (LHC) are continually upgraded to achieve greater sensitivity, paving the way for discoveries beyond dark matter. Innovations in detector design, such as cryogenic techniques and ultra-pure materials, are already being applied to explore other unanswered questions in physics. These advancements not only enhance our ability to detect dark matter, but also improve our capacity to explore phenomena like neutrino oscillations, proton decay, and the asymmetry between matter and antimatter. The discovery of dark matter would necessitate extending the Standard Model to include new particles interactions and symmetries. Such an extension could reveal connections between seemingly unrelated phenomena, such as dark matter and the Higgs field, provide a framework for understanding other cosmic mysteries like dark energy or the origins of matter-antimatter asymmetry, offer insights into the conditions of the early universe, such as the processes that occurred during and after the Big Bang. The breakthroughs in particle physics spurred by dark matter research would ripple across multiple disciplines from astrophysics to cosmology. These discoveries could redefine fundamental concepts such as mass force and even the nature of reality itself. As our theoretical frameworks evolve, so too will our ability to answer deeper questions about existence. As we conclude this journey through the unseen universe, one truth remains abundantly clear: dark matter is one of the greatest mysteries of our time. Its discovery and understanding hold the potential to reshape not only physics, but our very perception of reality. Yet for all that we've explored, its gravitational fingerprints, its hypothesized particles, and its role in the evolution of the cosmos, dark matter remains tantalizingly elusive. This mystery is a reminder of the vastness of the unknown. The universe is far larger, more complex, and more wondrous than we can currently imagine. Dark matter is but one piece of a much larger puzzle, one that includes dark energy, the origins of the universe, and the fundamental nature of existence itself. The ongoing quest to understand dark matter is a testament to human curiosity and ingenuity. It represents the best of science, a relentless pursuit of knowledge driven by the belief that the answers lie just beyond our reach. With each experiment, each observation, and each theoretical breakthrough, we inch closer to uncovering the secrets of the cosmos. But dark matter is more than a scientific challenge. It's a source of inspiration. It invites us to dream, to question, and to wonder what lies hidden in the fabric of the universe. What new realms of physics await discovery? How will these insights transform our understanding of the cosmos and of ourselves? The future of dark matter research is bright, filled with promise and potential. Advancements in technology, from more sensitive detectors to next-generation particle accelerators, bring us closer to direct detection. New telescopes and space missions will map the cosmos with unprecedented precision, revealing the subtle influences of dark matter on galaxies and beyond. Meanwhile, theoretical physicists continue to push the boundaries of what is possible, exploring ideas that might seem unimaginable today, but could become the discoveries of tomorrow. Each step forward in the hunt for dark matter deepens our understanding of the universe, reminding us that the pursuit of knowledge is never truly finished. As we unravel this mystery, we'll inevitably uncover new questions, new frontiers to explore, new challenges to face, and new wonders to marvel at. So as we look to the future, let us embrace the mystery of dark matter. Let it remind us of the infinite possibilities that lie within the cosmos, waiting to be discovered. The journey to understand dark matter is far from over, but every step we take brings us closer to answering the fundamental questions of existence. What is the universe made of? Where did it come from? And what is our place within it? In the end, the greatest discoveries often begin with the simplest yet most profound realization: the universe is far more mysterious than we could ever imagine. And that mystery in itself is the ultimate source of wonder.